This lesson is for Advanced Algebra, Lesson 3.3 on graphing linear combinations. A quick reminder that a linear combination is set up as ax plus by equals c. Another quick reminder is that the number next to x in this equation is not the slope, and the number next to y is not the y-intercept. However, we are going to learn two ways to graph this equation today, along with a quick mention of a third method. When students are asked to graph anything, they are always allowed to simply make a table. To make a table, you fill in some numbers for x, usually some nice easy numbers to work with, including some negatives and some positives. That's not going to be our focus today. Instead, I'm going to have students practicing making a zero table, which means they'll simply plug in 0 for x and for y. Students can also solve the equation for y or put it into slope-intercept form and then graph it from there. So we're going to practice and utilize both methods today in the examples. When you make a zero table, you make a small table of x's and y's with one of the coordinates being 0 for x and the other coordinate having a 0 for y. One of the benefits of making the zero table is that the two coordinates that you're going to be finding are the intercepts for the graph. When you plug in 0 for x, you'll be obtaining the y-intercept value, and after you plug in a 0 for y, you'll be able to identify where the x-intercept for the graph is. It's usually a good idea to utilize this method for graphing when you recognize that the a and the b values are easily divided into the value of c. For example, in this equation, 2x plus 3y equals 6, both 2 and 3 go evenly into 6, and so making a zero table would be a good idea here. So let's go ahead and give it a try. If I plug in 0 for x into the equation, I'm going to have 2 times 0 plus 3y equals 6. Hopefully students know and are comfortable with the idea that 2 times 0 is simply 0. And so what happens then is when we plug in 0 for x, what basically happens is that the 2 and the x and the 0 all cancel out, leaving us to simply solve 3y equals 6. To solve for y, we would divide by 3, and so we get a value of y equals 2. So when x was 0, y is going to make a 2. Keep in mind that that is a coordinate, 0, 2, and it is the y-intercept for the graph. Let's go ahead and do the same thing now by plugging in 0 for y into the equation. We go back to the original equation and we substitute a 0 for y. If you do 3 times 0, you get 0, and 2x plus 0 is simply 2x. So now we're simply solving 2 times what is 6. To solve for x using algebra, we would divide both sides by 2, and so we get x equals 3. So the other coordinate that we arrive at is the x-intercept, and that coordinate is the coordinate 3, 0. It is simply coincidence here that the numbers that we got are the coefficients from the original equation. That's not always the case, and students will see an example of that in one of the later examples. Let's go ahead and graph this now. And what's nice about these two coordinates is we know exactly where they will be. There's no guesswork involved. 0, 2, simply be careful here. No x value, and a 2 for the y value means we're going to go up 2. There's no slope involved here, we're simply just graphing a simple coordinate. The other coordinate is 3, 0, so we're going to go over to the right 3, and we're not going to go up or down, because there's no y value. Now when you connect those, you get your straight line. No other coordinates are needed, and calculating the slope is also not needed in order to make this graph. We have the intercepts available, we can graph them, and simply connect them with a straight edge. Another option for students is to take the equation and resolve it so that y is alone, which will simply put it into slope-intercept form. Then, utilizing your skills from slope-intercept, you can graph it from there. So let's try that with this example. To try to get y alone, we want to subtract 5x from both sides. Keep in mind that this is typically how students write it, but I'd recommend flip-flopping these and putting the 5x first. So if we add negative 5x to both sides, I get a negative 5x, and then the 30 is still sitting there, and it is a positive number, so I want to add that. To get the y alone now, I would divide by 6. Everything gets divided by 6, and I would recommend that you do that separately for each number. So now my equation becomes negative 5/6x plus 5. Keep in mind here that the 30 divided by 6 won't always necessarily work out to be a nice whole number, but typically it is. Now if we go ahead and graph, we can just use our skills from the slope-intercept equation. We start with the y-intercept, which is the number that doesn't have the x next to it, and put a dot. I need to make my graph just a little bit larger there. 1, 2, 3, 4, 5 is the y-intercept. The slope is the rise over the run. The top number is negative, so I'm going to go down 5, and to the right 6. And again, I need to make my graph a little larger. And I can go ahead and connect those to make my line. So I'd like students to practice this a little bit further. I'd like students to try both methods for graphing this equation here, making the zero table and then graphing those, as well as solving for y and seeing that that would result in the same graph. So students can pause the video right now and try that on their own, and I will demonstrate as well. First, I'm going to make a zero table. If I plug in 0 for x, I get 3 times 0, which basically makes that go away. If I solve that now for y, I divide both sides by negative 4, and I get negative 6. Starting over, I plug in 0 for y, I get 4 times 0, which makes that part go away, and I'm solving 3x equals 24. If I divide both sides by 3, I get 8. Again, keep in mind here that the numbers that I got don't necessarily coincide with the original coefficients in the equation. If I go ahead and graph that now, I need a coordinate at 0, negative 6, which is down. And I need to scroll down a little bit here. 1, 2, 3, 4, 5, 6. And over to 8, 0. And if I connect those, I get my equation. Now let's also go ahead and solve this equation for y. So I'd add negative 3x to both sides, and divide both sides by negative 4. Negative 3x divided by negative 4 is going to be positive 3/4 x. 24 divided by negative 4 is going to be negative 6. So I do get the y-intercept being the same at negative 6. From there, I would count up 3 and over 4, rise over run. So if I count 1, 2, 3 up and over 1, 2, 3, 4, I do end up on my line like I anticipated. If I count up again, up 3, over 4, again I'm graphing the exact same line as I did when I made the zero table. The students need to be comfortable with both methods. On the next question, this is not multiple choice. Students need to figure out which two of these are identical. So I'd like students to take a moment right now and solve all of these for y and put them into slope-intercept form. So I have all the answers here now for all of these equations solved for y. If students have questions about how those answers were arrived at, they can ask. And it's clear to see here that the two equations that are identical are b and d. Even though they looked differently as linear combinations, when you put them into slope-intercept form, they are indeed the same graph. One final question that I want students to work on is question number 8 from the homework. They ask you to write an equation in standard form. They give us two coordinates at -3, 0 and 0, -7. Hopefully students recognize that these coordinates are the x and the y-intercept. This one's the y-intercept, and the first one is the x-intercept. The only reason that that is significant is because the y-intercept is something that we know is going to end up being the b in the slope-intercept equation. So if we have the b, the only other thing we would need is the m. And we can find m by using the 2 points that they give us. Let's do the slope of the two coordinates. y2 minus y1 over x2 minus x1. When we simplify that, we get -7/3, and that's going to be the m. So now we have an equation in slope-intercept form. So I have -7/3 x plus -7, or we could say -7 there for the b value. So we have a really nice equation here. The problem is it's not in the proper format. To get it in standard form, we need x and y together on the same side of the equation. So to bring the x over to the y side, I would simply add the opposite. So if I do that, I get 7/3 x plus y equals -7. The -7 stays, the y stays, and the -7/3 moves over. I'm fine with students leaving their answer like this. However, the book does not think that that's okay. The authors of the book want you to eliminate any fractions that exist when you're writing standard form. To eliminate the fractions, as we've done in previous lessons, we will simply multiply by whatever the denominator is. In this case, the denominator is 3, so I'm going to take this entire problem and multiply everything by a 3 or by 3/1. If I do 3 times 7, I get 21. 3 times 1 on the bottom is 3. 21/3 makes simply a 7x. 3 times y is going to be 3y, and 3 times -7 is -21. This is the answer that the book will give for question number 8. I'm fine with students leaving their answer either in the orange form or the red.